Let's look at this GFG problem. It says print n-bit binary numbers having more ones than zeros. They will be giving you an input like this, and you have to output such things. So 111, 110, 101, right? What is common in all of this is if you take any of the input like 101, then if you generate all of its prefixes like 1, 10, 101, in each of these prefixes, you can see that the number of ones which are there, they are greater than or equal to actually number of zeros, right? So that is what they want. They want a list of such things, right? They want a list of such numbers. So another combination could be 110. So here the prefixes would be 111, 110. Here, so in each of the cases, you can see that the number of ones is greater than or equal to the number of zeros, and that is what they want. They want a list of all such numbers. Now, the easiest way to do this is using brute force. So they are given or they have given n, right, n as an input. What we can do is we will generate all the combinations. So let's say n is equal to 4, then 1, 2, 3, 4. So here there could be two digits like either 0 or 1. Here also two choices. Here also two choices. Here also two choices. So we have 2 raised to 4. So for n, we would have 2 raised to n such numbers, right? And when you get one such number, one such combination, let's say 1101 or something, in that you check all the prefixes. Okay, you check all the prefixes like 111, 1101, sorry, 1, yeah, and 110. So you check all these prefixes and check whether number of ones are greater than or equal to the number of zeros. Okay, so how many such prefixes would exist? You can see that there are n such prefixes, right? So in the brute force way, you would actually try out all possible combination, and in all possible combination, you will be checking its all of the prefixes, right? And after that, you will do sorting. So you will sort all of these elements and then try it, and then that will be the output that you will give. Okay. So that is what a brute force is. But can we do better than this? That is the question. Let's try this out. So my uh, logic over here is I will try to generate something like, okay, so let's try to solve this. Now my logic over here is, let's say I will try to generate the combinations in such a way, all of these combinations in such a way that it does not violate, right? I will never generate something like 100, okay, because you can see like this prefix is okay, this prefix is okay, but this prefix is not okay, or even like 1001, right? Because this prefix is not okay. So I will never generate such a thing. Okay. Whenever I'm generating, I will always take care that my rules which are there, they are not violated. And for that reason, I will be using a very simple concept. So whenever at any of the place you put a one, I will add a token. Okay. Let's say this is some kind of system, and in that system, I am adding some kind of token. Now, the number of tokens which are there, they will suggest me how many number of credits that I have. So if I want to place a zero, okay, before me, I should be having at least a one extra one. Okay, at least I should have one extra one. That means I should be having at least one token, right? So I can put a zero. So here you can see before that zero, I have a one, right? Let's say if I say 10, now what can we say about this? So when I added this one, I had put a token, okay? But when I added this zero, that zero consumed this token, okay? Now my system is empty. So I cannot really add any kind of zero because if I add a zero over here, this violates my condition, right? that the number of zeros over here are actually crossing the number of ones. So in a way, I can say that my credits which are there, they will go negative, right? So I don't want that, right? So this is how, so this is the base thing now. This is how we will proceed. So what I'm saying is, if I'm having n is equal to 4, let's just try to generate in a in a way that it will not violate anything. So right now I will start with a credit system of 0. So I initially don't have any credits, right? It's because the number of ones is equal to number of zeros. So all of these zeros are matching with these ones, right? Like if I have like two ones and two zeros, this zero will take up this one, this zero will take up this one. So eventually I don't have any credits, so my credits are zero. So here, if you see, I'm going to start with credits 0, and these are my indexes, let's say 0, 1, 2, 3. So since I don't have any credit, the only possibility for me is to put a 1 over here. Okay. Now, see over here. If I put a 1, my credits will be increasing. Okay, so my credits right now is 1. Now, I will go and see for the position number 2. Okay, for the position 1, I have stated. And you should be knowing why am I going in this direction. It is because of the prefix system, right? So the logic over here is if I make my prefix I minus 1 to be correct, then my prefix I would automatically be correct. Okay, I have to check those conditions, but that is the logic, right? This should be correct in order for my PI to be correct, right? So that is the logic. That is the reason why am I going from left to right. So now let's check for the location number 2. Now in my system, I have one credit. So I have two possibilities. Okay. Either I can use that credit. Okay. So if I use that credit, that means I will put a 0. And right now my credit will be 0. Correct. Or I can put one more 1 and my credits will actually increase. Okay. So here the credit plus plus will happen. Here credit minus minus will happen. Okay, because I put a 0, and credit plus plus because I put a 1. Okay, next again let's go to the next phase. So 1 1, because I have a credit, I can actually put a 0 or a 1. So let me put a 1, credit becomes 3, or I can put a 0 and credit will become 1. Correct. Again two possibilities, 1 1 1, again 1, credit becomes 4, 1 1 1 0, credit becomes 2. Now here also I think the same thing, right? 1100, sorry, 1101, credit is equal to 0, and 1100, the credit will be 0. Here actually credit will be 2, and here credit is 0. The same thing can be check over here, 100. Okay, so see over here, there are no two possibilities. Only possibility over here is to put a 1. Why? Because I don't have any credits, right? I cannot put a 0, right? So that is the reason I have to put a 1. There is no other possibility. No other possibility. Okay. So that is why credit is 1. Now because the credit is positive, again two possibilities could exist. So that is 1 0 1 1 1 0 1 0. Correct? So at the very last stage, if you see, I have completed all of these things. Correct? So I can put it all of these things into answer. You can check any of these combinations. Nobody of them will be violating the prefix system because whenever I was making a prefix, I was taking care that if I do not have any credits, do not put 0. Okay. So my prefix I minus 1 was always correct. And because of that, my prefix I is also correct because I'm taking care of this credit system. Okay. And do I need to sort after this? The answer is no, because whenever I am making any combination, the first combination that I am going to try is 1 and then 0. Okay, so then 1 and then 0, right? Then 1 and then 0, 1 0, like this. So that is the reason you can see that it is already sorted. So 1111, then comes 1110, then comes 1101, then comes 1100, like this. Okay. If you had done it the other way, like if you just try out the zeroth possibility first and the one possibility later, then yes, you would need to sort. Okay. So that's the whole logic. Okay. You can do this simply using recursion. So if I say this is a call, this is the starting call. So let me be like solve int I. Okay, so there will be some kind of I and there will be some kind of credits that I have, right? And yeah, that's it. Now, if you see over here, if my I actually becomes n, then I have to return. Okay, but before returning, I will actually also store the answer. Okay, because see, 2, 3, 4. So 0, 1, 2, 3. And my n is equal to 4, right? So whenever I am over here at 4, but I have only n is equal to 4, right? So whenever my I gets to 4, I have to stop, right? So that is the reason I is equal to n. And because I know that I've already made a combination which actually exists, right, which actually follows the rule, I can actually add this up into my answer as well. Okay. Else I am somewhere into the between, then I will check if my credits are actually, greater than zero, then then I can try out both the possibilities, right? I can do it like solve I minus one, so sorry, I plus one and credits plus one. If I try out 1. Okay, so let's say over here I am having some kind of binary. So the binary could be like over here the binary is 1 1, right? So I will be passing on this 1 1 over here so that if we are taking a 1 or a 0, we can append to this 1 1, right? So that will be 1 1 1, and here we are appending 0 to this 1 1, so that will be 1 1 0. So here it would be like binary, some kind of binary, and I'm passing 1 to it, right? Some kind of binary, and I will be passing 1 to it. And then, so this is the one combination, but because I have a positive credits, I can also put a 0. So I will also have this call I plus 1, but because I have taken 0, I have to do a credits minus 1. Okay, credits minus 1 and binary plus 0. That is correct. Now, if that is not the case, else my credits would be 0. Okay, my credits would be 0. So if I don't have any credits, there is only one combination that I can do. That is solve I plus 1 credits plus 1 because I will be adding a 1 and binary plus 1. Okay, that is the only combination I can do. That's it. This is the whole code. So what is the time and the space complexity for all of this? So the time would be actually order of 2 raised to n, okay, because you would be either trying out two or one possibility. So even if you consider two, that will be like order of 2n because you can see over here the whole diagram is almost like a binary tree, right? And what is the space? Space complexity would be if you see over here, what is the height of the tree? The height of the tree is almost n. It is n. And at each stage, we would be having like a binary, you know, which will be storing this 1 1 over here. Then here also it will be storing like 1 1 0, something like that, right? So at each stage, we would be having some n storage, right? So n height into n storage, which is almost like n square. Like almost we can say order of n square space I have, and time is order of 2 raised to n. So let's just see the code. So you can see here is where it starts. So I'm going to start with the zeroth index, okay, and with the 0 credits. with nothing as my output and the n. So when I go to the recursion part over here, it says that if I is equal to n, I have actually reached the boundary and I can push back whatever is there inside my string into the answer. Else, I can have solve of I plus 1, credits plus 1. So here, binary plus 1, whatever the string I had, I'm putting a 1 over here. And because I'm putting a 1, I'm just incrementing the credits. And I'm going to solve from I plus 1, right? So at that ith place, I have just stored a 1. And if I do have credits to be greater than 0, then we can also try this combination where I put a 0 at the end and I just minus the credits. Okay, so make sure that you write this later and this first, because see, if you do this, so it will not be ordered as you can see over here, right? So expected output is 1110, but you are having 10. That is because you are trying out the zeroth combination first. Okay, but you want a sorted combination, so always try the first combination first and then the zeroth. Right, so it is working. Let me just submit. Yeah, so that works. Okay. So yeah, that's all for this